Good evening. We are Group 8, and today we are excited to present our practice module project, an AI-driven portfolio allocator, which is a system designed to help optimize investment decisions using artificial intelligence. In our project, we aim to combine financial insights with machine learning techniques to create a tool that demonstrates both practical value and technical innovation. Here's our agenda for today. We'll begin with a brief introduction to our project, followed by an explanation of our overall approach. Next, we'll walk through each step of our process leading up to the final model. After that, we'll provide an overview of the system and discuss potential areas for improvement. Finally, QQ will conclude with a recorded demo, showcasing how our AI portfolio allocator works. The key challenge many financial professionals face is constructing a stock portfolio. Traditional methods often struggle to balance risk and reward. Experts may know which stocks to buy, but the real question is, how much should be allocated to each one? Our goal is to use AI not to replace human judgment, but to enhance it, by recommending optimal portfolio weights for each stock, helping experts make more data-driven and disciplined allocation decisions. Our approach starts with understanding why most systems fail. Financial markets are extremely noisy. Yet, many models try to capture everything with a single prediction. And that's where they break down. What makes our approach different is how we decompose this complex problem into two key parts. First, we predict direction, where the stock is likely to move and with what level of confidence. Second, we estimate volatility, how risky or unstable that movement might be. By separating these components, our model can focus on the key drivers behind market behavior, making it both more interpretable and more robust. Our data preparation process is designed for the model to focus on key features in financial prediction, direction, and risk. We started with two key targets. First, price direction, a binary classification of whether the next move is up or down, along with its probability. Second, price volatility, which we measure using the Yang-Zhang estimator. This captures both overnight and intraday fluctuations, giving us a more realistic sense of market uncertainty. We initially explored expected returns, but later excluded them. The signal was too noisy and unstable for consistent learning. On the input side, we combined statistical and behavioral features. The statistical features include momentum and volatility across multiple time horizons, allowing the model to detect persistence and regime shifts in price movements. The behavioral side covers technical indicators like RSI and MACD, as well as VIX-derived signals, which reflect market sentiment and investor psychology. By engineering the data this way, we ensure that the model learns not just from price mechanics, but also from how the market behaves. After feature engineering, we ended up with a large number of indicators, many of which were correlated or overlapping. So, our next focus was to retain the important features. We used a two-step selection pipeline. Step 1. Correlation filtering. We removed any features with a correlation above 0.9. This helps reduce redundancy and multi-collinearity, ensuring that each feature we keep contributes unique information rather than repeating what another feature already tells us. Step 2. Statistical selection. We rank the remaining features based on their linear relationship with the target, using statistical relevance tests. This allows us to retain the most predictive signals while filtering out weak on noisy ones. Together, these steps create a cleaner, more focused, and more interpretable feature set. Moving on to our prediction framework, which went through a major revamp. Initially, we tried to predict expected returns directly. In this setup, the predicted volatility was used as an input feature to inform the return forecasts, based on the idea that higher uncertainty often comes with higher potential returns. However, in practice, this approach struggled even with advanced ensemble and gradient boosting models. So, we shifted to a segregated approach. Instead of predicting returns directly, we built two separate models, one for direction and another for volatility. This separation makes the system both statistically more stable. The direction model focuses on recognizing patterns in market movement, while the volatility model quantifies uncertainty, together forming a more interpretable and reliable foundation for portfolio decisions. Here's a visual summary of our prediction framework. On the left, you can see our initial approach, where the forecasted volatility was used as an input to predict expected returns. The idea was to link uncertainty with return potential, but as we found, the results were unstable and difficult to generalize. On the right, we have our finalized segregated approach. Here, we replaced return forecasting with a directional classification model and treated volatility as its own independent prediction task. This separation allows each model to specialize, one capturing market direction, the other risk behavior, giving us a more robust result. For our model evaluation, our metrics were chosen to match the nature of each prediction task, direction classification, and volatility forecasting. Starting with directional classification, we use AUC. AUC measures how well the model can distinguish upward from downward moves across all probability thresholds. It's robust to class imbalance and overlapping signals, both of which are common in financial markets. Most importantly, AUC focuses on ranking performance rather than raw accuracy, which makes it a far better indicator of predictive power in noisy environments. For volatility forecasting, we evaluate using RMSE. This captures the average deviation between predicted and realized volatility, and it penalizes large errors more heavily, an essential feature for risk-sensitive predictions. We avoided using R-squared, as it tends to become unstable under regime shifts, making it unreliable in volatile market conditions. By aligning each metric with the statistical behavior of its target, our evaluation framework measures practical reliability meant for financial datasets. This slide shows the trial evaluation results for the initial framework. For volatility forecasting, the CatBoost model achieved the best RMSE at 0.0596. For expected return forecasting, the distributed random forest model delivered the best RMSE at 0.0539. This slide shows the final evaluation results for both models after hyperparameter tuning. For the directional classification task, the CatBoost model achieved the best performance with an AUC of 0.735. For volatility forecasting, the random forest model delivered the lowest RMSE at 0.0539. First, financial experts like yourselves decide which stocks to include based on your own fundamental research. Next, you enter our app and input your selected list of stocks through the user interface. On the back end, the system fetches live market data for each stock, generates the necessary features, and predicts both direction and volatility. Based on these predictions, it calculates the recommended portfolio weightings, which are then displayed back on the front end for you to review. QQ will dive deeper into how the application works in practice during the demo. Looking ahead, there are several avenues to enhance our system. First, we plan to incorporate alternative data, such as news sentiment and macroeconomic indicators, to account for signals outside of the traditional datasets. Second, we aim to explore an ensemble decision layer that aggregates outputs from multiple models, potentially improving prediction robustness and reliability. Finally, we want to add feature attribution analysis to provide transparency, helping users understand why certain allocation decisions are recommended. These improvements will make the system both more robust and informative for portfolio management.
Welcome to BearlyProfitable, your intelligent portfolio analysis platform. Today, we'll walk through the complete user journey from building your portfolio to getting data-driven insights and predictions. Let's dive in. Users are welcomed by a sleek glass-morphic interface and guided through three simple step processes. First, we have our stock selection, where users can choose from expert-created portfolios or use a real-time search powered by Polygon API to find stocks and view live data. In this example over here, we'll choose the tech giants as our example. Next will be our portfolio allocation. We're able to set a total portfolio value and assign stock weights using intuitive sliders, or even just click the equal split button over here. Next, we have our review and launch section. So we are able to view a summary of allocations and portfolio details, then click launch analysis over here to start the intelligent processing pipeline. Now the magic happens. Behind this dancing bear, our comprehensive guideline executes in 4 stages. In stage 1 and 2, we will first collect real-time and historical data with smart caching. It will then perform feature engineering to create technical indicators like moving average and RSI, momentum and volatility measures. In stage 3, we train 2 machine learning models per stock, a cat boost classifier to predict price direction and a random forest regressor to forecast volatility. Using 5 years of historical data and around 30 engineered features, these models generate 5-day forward predictions with confidence scores, providing both trend direction and risk insights. In stage 4, the platform performs portfolio optimization by analyzing stocks' correlations and compute key metrics like expected returns, volatility, Sharpe ratio, and diversification. Users then land on the comprehensive portfolio dashboard. The portfolio dashboard gives users a complete view of their investments, showing real-time portfolio values, daily changes, and top-performing stocks. An interactive performance chart displays historical and model forecasted prices over 5, 10, and 15 days periods with a confidence-based color coding. User can also compare 3 AI-optimized strategies. We have our conservative, balanced, and aggressive portfolio strategies to tailor to their portfolio approach. Portfolio weights are determined using the modern portfolio theory formulas. The AI Insights panel over here is powered by a large language model to analyze the portfolio data in real time and provide actionable recommendations. It compares current and recommended allocations, reviews stocks performance and strategy type, then delivers clear suggestions with explanation and projected outcomes. In our rebalancing section over here, users are given suggestions on what to do with their portfolio in order to achieve their desired risk level. For example, they should buy 9 Apple shares over here and sell 1 Google shares. Users can also drill into any of our stocks. So, for example, Google. Right? So by drilling into any of our stocks, we're able to see the deeper analysis for the specific stocks. So the price prediction chart displays a 5 days forward price target, complete with a model performance score at the bottom over here. All predictions are generated from the trained cat boost and random forest ensemble, stored in the backend for instant access. To summarize, BearlyProfitable is more than just tracking the app. It's a sophisticated system that automates institutional-grade analysis, utilizes an ensemble of well-trained models, and presents the results in a beautiful and user-friendly interface. We give you the edge to ensure your portfolio is never just barely profitable.